that's going to be the end of the Italian, I'm afraid. Okay, so what I'm going to do this evening is to talk through after 8. And by that I mean what has happened since JDK 8. And what I always like to do when I start these presentations is to ask you, the audience, so who here is using JDK 8? Okay, most people. Good. Okay. Who's using JDK 11? Okay, good. A few people as well. Anybody using JDK 12? 13? Okay, a couple of people. Interesting. Let's go back the other way. Anybody using JDK 7? Nope. 6? Good. I'm hoping that nobody is using anything older than 6.
Java 5?
1.41. Anyway, so what has happened since JDK 8? Now, if we look at JDK 9, I'm not going to spend too long on JDK 9 because that's been around for a while, but it's worth just spending a couple of minutes talking about this, because JDK 9 was a very big change in terms of Java, not just from a technical perspective, but from the point of view of how Java is developed and how it's delivered. So JDK 9, Oracle will tell you, was the last major release of Java. And by that, they mean the last release that had several years of development work that went into it. And so I borrowed this slide from Oracle. I figure I used to work for Oracle, so they owe me a few slides still. And it lists all of the features that went into JDK 9. And there are about, I think on that list, there's about 86 new features that went into JDK 9. Many of them quite small. Many of them are sort of in the JVMs, you don't really notice them too much. But obviously in JDK 9 there was one big change which has a real impact in terms of how we migrate applications from JDK 8 or earlier to JDK 9 or later. And that is modularity. So again, I don't want to spend too long talking about modularity because it's been around for quite a while now and people have started experimenting with it, they kind of got used to it. But it's worth just spending a couple of minutes talking about what modularity really means in terms of the JDK and the impact it has on moving applications. So you can think of modularity as being two distinct parts. The first part is really good and really useful. The second part, we'll come to that. So the first part is saying that if you look at the history of Java, did anybody here use JDK 1.0? A good couple of people. That's bad. Doesn't make me feel too old then. So I remember JDK 1.0, and I went back and I looked at it, and there were 211 classes that you could use from the class libraries to develop your applications. That's not a particularly big number. Now, if you move all the way to JDK 8, there's about 8,500 public classes in RT.jar, which is great for us as developers, because now we don't have to write the ArrayList class every time. We don't have to write semaphore class. It's all there for us. But the problem is that going from 211 classes to 8,500, they put them all in one file. And I can't think of a single application, and I think I should run this as a competition. Find an application that uses all 8,500 public classes in the class libraries. So it doesn't really make sense to have them in one big file. It's monolithic. We don't like monolithic things anymore. So the idea of modularity is about breaking up RT.jar into more manageable pieces. And if you think about Java, we've always had this idea of grouping classes together. So we've had packages. Set of logically related classes, you put them in a package. Modules takes that to the next level, so we group logically related packages into a module. And the way that they did that was they looked at the different aspects of the class libraries, and they ended up with 75 modules in OpenJDK. If you look at the Oracle JDK, there's a few more, but OpenJDK has 75 modules. Now, of those, 24 are necessary just to be Java. So these are the core part of the Java libraries that you need to conform to the Java SE specification. Then there are two aggregator modules. Now, aggregator modules are ones that don't contain any packages, but only contain references to other modules. And we'll kind of come back to that a little bit later on. Bizarrely, smart card as a module is in there, and that's a kind of historical thing from when Sun, I believe it was, decided to include the smart card functionality into the Java SE platform. And then there are 48 which are JDK specific. They relate to all the tools, they relate to all the things that are not part of Java SE. So that's all the good side of modularity. But then the other thing that Oracle decided they wanted to do, and the developers OpenJDK, specifically Mark Reithold, they said that they wanted to encapsulate the internal APIs. And so if you look at rt.jar, 4,500 public classes, but there's also a number of other classes in there which you're not supposed to use. And Sun and Oracle have always been very clear about this. They didn't document them. They said, no, you're not supposed to use them in general applications. And the most famous or infamous of those is Sun-Misc Unsafe. Now, I really like Sun-Misc Unsafe because the clue is in the name. Unsafe. Don't use it. But has anybody here used Sun-Misc Unsafe in their code? Okay, a couple of people. Has anybody here used a third-party library or framework like Spring or Hibernate or Log4j? Yes. Okay, so you have used Sun-Misc Unsafe. It's just that you don't know about it because you're using the framework. So what Oracle wanted to do was to turn off access to these APIs, to make Java safer, to make it easier to maintain, and so on. But people obviously said, well, if you do that, things like Spring and things like Hibernate will be broken, and lots of people use them. So Oracle said, okay, we will let you continue to use these, and there are some command line options you can use to turn on different aspects of the internal APIs, whether it's from including them from a package or whether it's using them from reflection. At the moment, the default is to allow you access to the internal APIs. And I saw an email today on one of the aliases which said that apparently at JFocus, which was also on this week, that Mark had said that as of JDK 16, they are setting the default to off. So you'll no longer be able to use the internal APIs by default in JDK 16. I find that a little bit surprising, and I'll be interested to see how that works in practice. But that's what they're going to do. Now, the good thing about modularity is the ability to build a runtime for your application that is tailored just to your application. If you think about microservices where we're deploying into a container, like Docker, then this makes a lot of sense, because what you can do is you can say, okay, I've got my service written in Java. What I do is I build a runtime that only includes the modules that I need for that application. And if we look at this simple example that I created here, we do JLink, and we tell JLink where the modules are located, both for JDK and for my application. We say that we want to start with this particular module, which contains like my entry point, and the output directory is my image. If we run that, we'll end up with a directory which contains subdirectories that look exactly like the JDK. So it's got a bin directory, a conf directory, a lib directory, and so on. If we go into the bin directory there, and we run Java, and we say list modules, what we'll see is only the modules that we need for that application. So in the case of the JDK ones, I've got Java Base, which I have to have because you have to have Java Base in everything, Java Logging, Java SQL and XML, and then I've got the 3 modules that I created for my application. Now you can do this without having modules for your own application. So you can leave everything on the class path, you can do some analysis yourself, and then create the runtime manually by saying which modules you want to include. The nice thing about this is it can really reduce the size of your Java runtime. If you look at the standard JDK, it's about, well, on Linux it's about 330 megabytes. If you make the simplest possible application, hello world, and you strip out the symbol tables, you strip out the manual pages and things like that, you can reduce it to about just over 10 megabytes. as the JDK. Now, clearly, as you add more features in and you use SQL and logging and so on, it will get a bit bigger. But it really is a factor of, or an order of magnitude, reduction in terms of the size of the JDK. So it's very good for the idea of things like microservices and deploying into containers. Very importantly, Oracle said that another big change in JDK 9 was about compatibility. We've always been used to taking applications that were written on older versions of Java and just running them on newer versions. And that's worked pretty well in the past. I know I've actually taken code that's written on JDK 1.0, and some of it will even run on JDK 8 without recompilation. Not all of it, there's some weird class file changes that got made in JDK 1.1, but a lot of code will just move straight away. Oracle have now said that clean applications that just depend on java.se should just work. It's a little bit less than reassuring. I'd like to see it will just work. But in this case, they say it should just work. And the reason that it should just work is because there are a number of things that Oracle have started to do in terms of removing features as well as adding them. So we've had deprecation right from JDK 1.1, about 450 API elements that have been deprecated up to JDK 8, and up until then, nothing had ever been removed. So in JDK 9, they removed the entire 6 methods. That was it. They've then gone a little bit further with JDK 10 and JDK 11 and so on, and we'll come back to that in a moment. But it is important to understand that they are now starting to remove features as well as add them. And like I say, this was about cleaning up the JDK. So we've had deprecation since 1.1, as I said, 453 elements deprecated in JDK 8, and we haven't removed any of them. In JDK 9, like I said, they removed 6 methods, and the reason for those 6 methods, because of course you look at that and you say, what did those 6 methods do that was so bad that meant they had to be removed in JDK 9? And it turns out that when they came to separate out the modules in the JDK itself, they found some very odd relationships between different parts of the libraries. The reason being that when people had written new libraries, they'd simply looked at everything that was in the rt.jar and said, we can use anything in there, it's fine. But that ended up with some odd relationships. For example, and the bean descriptor also includes an icon. Icon needs to be rendered, so you need Java 2D, which is part of the desktop libraries. So things like that. So removing those 6 methods enabled them to make a somewhat cleaner separation of the modules within the JDK. They also removed some other things. There was a class that was removed from the Java of that, and nobody put their hand up. So it is somewhat reasonable to say to Oracle, okay, that's 2 different garbage collectors which are very similar. They don't want to maintain them both. Nashorn, PAT200, those are all deprecated, and will probably be, well, PAT200 is also removed in JDK 14. Nashorn, at some time in the future, it's also going to be removed. And I suspect that there will be others that will end up being removed in the future as well. So the key thing here is that compatibility is not guaranteed in the same way. And again, Oracle have said, new versions of Java may include breaking changes. What they've also said is that they will announce anything that's going to be removed by deprecating, not just the API, but also the features, and they will give us a very healthy minimum of 1 release warning between a feature being deprecated and it being removed. Now, if that's very good of them, because if they gave us less than 1 release warning, that would be no warning at all. But it does mean that it could be only 6 months between a feature being deprecated and a feature being removed. So it's just something to be aware of. Okay, so let's move forward into JDK 10. Now this was the first release that only had 6 months of development work behind it. So clearly, we weren't going to get as many new features as we got with JDK 9 or JDK 8. But we did get some interesting new features. And the one that's really kind of good in JDK 10 is local variable type inference. So this is very common code that we have in Java. So So we're using local variables, and we say, okay, I want a list, and so I'm going to create a user list, which is an array list. And in order to create that, I need to define it this way. I need to say array list of type string, user list equals new array list. And in this case, since we're using JDK 8 and later, we could also use the diamond operator. So at least we don't have to specify the generic type parameter twice. But we do have to specify the type twice. So we get array list. It's both sides. Similarly, if I want to retrieve a stream from that list, I need to explicitly state it's a stream of type string, and the variable is called string. I can use the for loop, and I can say, okay, string name over the user list, and I can use the for loop in the old style and say for int type 0 by less than 10 I++. In JDK 10, we now have local variable type inference, and that means that we now have var, great, just like JavaScript. Maybe not so great. But what it means is we can do this. So rather than having to specify the type of the user list as being an array list of type string, we simply say var, and we let the compiler infer the type for us. So now we say new array list, and very importantly, we have to change, because we had the diamond operator before, and this is a really important thing to get across, because if you go through and you refactor your code, do not just go down the left-hand side of your code and go, just change everything to var. You have to be very careful, because if you've used the diamond operator, you bump into double type inference. Because if you left that with the diamond operator, the compiler would go, how do I infer the generic type parameter? There's no information there, so I will make it object. So you end up with an array list of object rather than an array list of string, and that could well change the way your code works. So now you have to remember that if you use the diamond operator and you want to use var, you need to put the specific generic type parameter in there. So that will infer an array list of type string. Similarly, we can use var with stream, and that will infer a string of string. We can use var in a for loop. So we can say for var name over user list, and again, the compiler will logically infer that the name is string. And lastly, we can do this, where we can say for var I equals 0, and so on, and it will infer int. Do not do this. This is a very bad example of where to use var. The reason I say that is because var has 3 letters. Int has 3 letters. You are not saving anything by using var in that instance. It makes it harder to see what's going on, so use int instead. There are some nice places where we can use local variable type inference. Try with resources block. Now, I've deliberately made this quite verbose, lots of text in there, but I've used reasonable variable names here, and so we end up with input stream equals socket.get input stream reader, new input stream reader of input stream, buffer reader, new buffer reader, input stream reader. All quite complicated, and you have to look at the code quite carefully to understand what's going on. If we use var, we can eliminate a number of those type definitions, and we can make the code a lot clearer and a lot easier to see what's going on. Because var lines things up nicely, and so suddenly we see, okay, input stream reader, buffer reader, all good. So that's a good example of where you might want to use the local variable type inference. Now, local variable type inference has some interesting edge cases, and this is one of them. This code will not compile in Java. What we can do is we can create an inner class, and we can say, okay, object fruit equals new object, and then within that we want to define an extra variable called name, apple, and then we want a new method in French. You tell what I last did this presentation, I was in France, and we return pom. Now, funny enough, that bit of code will compile. There's nothing wrong with that in terms of the Java syntax. I found that a bit odd when I first looked at it, and it was like, yes, that will compile. But if we want to try and use the variable or the method in that object that we just created, that won't work. The compiler will reject it. It'll say, hang on, you've got an object. If you try and reference fruit.name, name is not a part of object, inference is not a part of object, it won't work. But we can make this code work if we use var. So if we say var fruit equals new object, and we do that, and then we reference it through this, that code will compile and it will work. And the reason for that is because of what are called non-denotable types. The JVM understands more types than the Java language can express. So in the case of this situation here, the compiler will actually generate a type which you can't represent in the Java language, but the JVM will understand. And so it can actually compile that code and it can make it work. Like I said, this is an interesting kind of edge case. There's also the ability to use an extension of this which is an intersection type. So you can have a type which implements two interfaces, and because you can't express that in Java, so if you want to express a type that implements two interfaces without creating a class separately, then you can use var again and it will actually work. So that's a kind of interesting situation for local variable type inference. One last thing about var, it is a reserved type, not a reserved keyword. What does that mean? Well, interestingly, something that you could have done in JDK 9, in fact, no, you can still do this. So you can have var equals new value reserve. And the reason for that is that var is a reserved type, non-reserved keyword, so you can still use it as a variable name, which is good, because I'm sure that there are people out there who've used var as a variable name and it would break the backwards compatibility if you didn't do it. However, what you can't do, which you never would have done in JDK 9, is create a class called var with a lowercase v. Obviously, the convention in Java is to use an uppercase v rather than lowercase v, so you can't do that anymore. But you can still create a class called var with an uppercase v. So technically you could have var equals new var, and that would work. I'm not sure you want to do that, but you could do it. In terms of JDK 10, there are a number of what are called JEPs, JDK Enhancement Proposals. And I haven't listed all of them here, I've just picked a few which are the ones that are a little bit more interesting. First of those is the fact that they've made the full GC part of G1 parallel. In the past, it used a single thread to do the full compaction, and people complained about that because performance compared to the parallel collector was not as good. So now they've made the full compacting part of G1 parallel. You can use multiple threads and it speeds it up. Application class data sharing used to be a commercial feature in the Oracle JDK, and now it's been contributed to the Open JDK, so it's now part of standard build Java. What this does is allow you to get faster startup time for your applications. When you start an application, the JVM has to load the class files for the code that you want to run. When it does that, it needs to build some internal data structures to represent those classes. When you start the application again, it does the same thing. It loads the classes, builds the internal data structures, runs the application. So with application class data sharing, you run your application and then you say, save those internal data structures. It writes them to a file, and then the next time you start the application, rather than having to read class files and build those structures, JVM simply says, use that file, map it into memory, point the data structures at that area of memory, and off it goes. So it reduces the startup time. The other thing that's nice about that is if you have multiple JVMs running in the same machine, because the file that you map in is read-only, the several instances of JVM can share that mapped-in file, and therefore it reduces the resources that are required by all those JVMs. In JDK 10, we have an experimental Java-based JIT compiler called Graal, not to be confused with the Graal VM. I have no idea why Oracle decided to call them the same thing. It's just like it doesn't make a lot of sense. So we have the Graal JIT compiler, and then we have the Graal VM. And technically, the Graal VM should be called the Substrate VM. because that's the project that it came from. But in this case, it's an alternative to the C2 JIT compiler that's actually written in Java. And the idea of writing in Java is to make it easier to maintain, easy to add new features. It is still experimental, so you can turn it on, you can play around with it. It's not recommended for production at the moment. Last one there is heap allocation on alternative devices. This was some code that was compiled and contributed by Intel. They've been working on storage systems that, like non-volatile RAM, that works at the same speed as dynamic RAM, and so the idea is to be able to put your heap on non-volatile RAM as well as on dynamic RAM. JDK 10 had a number of new APIs, and there were 73, but I didn't bother listing all of them. Some of the key ones are to do with collections, and specifically unmodifiable collections. So now the list, the set, and the map interfaces have static methods called copy of. And what they do is they take a collection, whether it's a list, set, or a map, and they return a copy of that, which is unmodifiable. So you can't change the elements in the collection. Similarly, for the Streams API, there are now 3 new collectors, which will allow you to take an input stream and then collect that stream into an unmodifiable list, set, or map. And lastly, they added a new method to the optional class, which is called or else throw, which does exactly the same thing that get, just has more letters in it. So I'm not altogether convinced why they added that afterwards, but apparently it's more descriptive, so people find it easy to understand what it does. JDK 11. Now, JDK 11 is the current long-term support release for the JDK. One of the things that Oracle said when they made all these changes, and the idea of a 6-month release cycle, was that having extended support for all versions of Java wasn't going to be manageable. So they've used the same approach that Ubuntu do, and so they're having one long-term support release every 3 years. So every 6th JDK is long-term support. JDK 11, current one. There wasn't so much that went into JDK 11, but one of the things they did was add the ability to launch single file source code. And the reasoning behind this is that if you want to get started with Java and you want to do like the very basic thing, like hello world, it's actually quite a process, because you've got to create your file, you've got to do, create a class, then you've got to do public static void main, string, brackets, args, then you've got to do system.out.println, hello world, then you've got to compile it, then you've got to run it. So there's all sorts of steps involved. Now, JDK 10 and earlier, there were 3 ways of starting the Java application. The simplest is from the class path. So you simply do Java on the CP where your classes are, and then the name of your class. You can launch from a jar file, so you can do Java -jar, then your jar file. And now that we have modules, you can also launch from a module. So you can do Java -m, then your module. In JDK 11, there's now a 4th way of doing it. So you can actually do Java on a Java source file. So Java factorial.java 4. When you do that, the JVM will look at factorial.java and say, hang on, that's not a class file. It doesn't have the magic number at the front of the file. Anybody know what the magic number for the Java file is? Thank you, very good, excellent, that's what I like to hear. So it doesn't have cafe name at the front of the file, so it says it's a Java file. In this case, I will now run Java C on it, compile the code into a class file, and then run that class file, assuming you don't have any compile errors. And it will pass the parameter to it to make the application work the way you want it to. This only works for one source file, so you can't have multiple source files, but you can specify the class path and put lots of libraries in. You can take that one step further, and you can use shebang support. If you put your code into a file and you make the first line of your file #bang, and then where your Java executable is, specify the source level you're interested in, make that file executable, then run it on Linux, for example, you can now do /factorial 4, and everything will magically work and it will compile and it will run. So we're almost at the point where we have Java scripting. Not JavaScript, but Java scripting. Not quite, but it's a little bit closer. Some selected JEPs that we had in JDK 11. First of these is nest-based access control. This is something which is completely invisible to developers. It's a thing that happens within the JDK and JVM itself. And the reason for this is to do with Project Valhalla. I'm going to talk about Project Valhalla at the end and talk about some of the bigger futures. But the idea is that for some of the things they want to do in Valhalla, the way that inner classes work, and specifically how an inner class can access a member of the outer class, which is marked as private, which is legitimate, the way that the JVM handles that had to be changed. So that's what nest-based access control is about. They then introduced the idea of dynamic class file constants. And I remember when I first saw this, I thought, that's not very logical. It's either dynamic or it's constant. It can't be a dynamic constant. That doesn't make any sense. But it does. And the reason for this is to enable people who are writing compilers for languages other than Java onto the JVM. Sometimes they need the ability to change the class file constants that are used. What this allows you to do, or the compiler writers to do, is to treat the constants in a class file like you have final variables in Java. So you can set the value once, but after that it's fixed. So that's the dynamic nature, is you can set the value once to whatever you want. But, question?
Inlining?
Inlining?
Of the constants?
Yes, I mean there's a whole set of things around this. So it's, like I say, it's really to allow people to write compilers on top of the JVM that use different features of languages unlike Java. So, yeah.
Once upon a time we had constants inlined in our reference with the classes inlined in, and so with this.
Yeah, I don't know. I haven't looked at it in that much detail, so I'm not quite sure how inlining would work with that. But yeah, you'd have to actually have a look at the JET to see what that actually does. Yeah. Next thing is the Epsilon garbage collector. This is an interesting garbage collector because it doesn't collect any garbage. So you think, okay, what's the point of a garbage collector that doesn't collect any garbage? And this was actually a collector that was introduced by Alexei Shibboleth, who works for Red Hat on the Shenandoah garbage collector. And the reason that it was introduced is primarily as a way of measuring the performance impact of a garbage collector. What you do is you run your application with the Epsilon garbage collector, so it doesn't do any garbage collection. Now, assuming you don't run out of heap space, you measure the performance of your application. Then you turn on your new garbage collector, which in Alexei's case is Shenandoah, and you then see what the difference in performance is, so you can measure the impact of how your garbage collection algorithm works. Some people have suggested that it could also be useful if you're doing things like AWS Lambdas or the serverless computing, where you've got very short-lived processes and you don't want the overhead of garbage collection because you know you're not going to run out of heap. I'm not totally convinced about the safety of that, but if you think it works, give it a go. HTTP client. This was introduced in JDK 9, support for HTTP 2. It was introduced as an incubator module so that it could be provided to people, they could give feedback if they thought any changes need to be made, and then it could be made part of the standard. So in JDK 11, they have now made it part of the standard. TLS 1.3 is just upgrading the security of transport layer to the current version. This is, we've actually backported this to JDK 8, and I saw a thing, I think it was yesterday, about how they're also going to allow backporting to JDK 8 for other things as well, so that will work. And then the last one is, sorry.
You as in Zulu?
Yes, yes. So Azure, we have backported TLS 1.3 to JDK 8. You can turn it on with command line flag. The thing that Oracle are now looking at doing is backporting it to JDK 8 and being able to use it from an API as well. So that's kind of extension. But yes, we have backported it to JDK 8.
And read it first.
or we do it first. Last one is another garbage collector, and this is the ZGC, or as the Americans like to refer to it, ZGC, which is a low latency garbage collector. This is quite similar to what we do with our Zing JVM. They've actually used some very similar ideas to what we've done there. It's still experimental. It is still single region. It's a single equal region, so it doesn't use generations. Some people I've talked to who've tried it, they say they get pretty good results with it, but it has a tendency to crash. So, as a production environment, probably not a good idea at the moment. Some new APIs that made it into JDK 11. Some interesting ones here. So there's input stream and output stream now have the ability to create null input stream or null output stream. Similarly, null reader and null writer. And I looked at this, and it's kind of like /dev/null. So you can read 0 bytes from the input stream, and you can throw as much data at the output stream, and nothing will happen to it. And I thought to myself, I've been programming Java for 24 years. I've never needed these APIs. Why were they added? And the reality is that if you look at the streams API and Lambda expressions, there are certain situations where when you're using a functional style of programming, that actually having the ability to create a null input stream or a null output stream is actually quite useful. So that's kind of the reason behind that. And they added another method to optional. In this case, it's isEmpty, which is clearly the opposite of isPresent. They're determined to add more methods to optional. String had some new methods added to it, so it came in for some updates finally. First of those is blank. I don't think I need to explain that. It's, is the string blank? That's it. There is a lines method that if you have line breaks within your string, then you will get a stream of the strings broken up by those line breaks. Repeat repeats the string by the number of times that you specify. And then there are 3 methods called strip leading, and strip trailing. And what they do is remove white space either from the beginning, the end, or both the beginning and the end of the string. The observant amongst you who've been programming in Java for a while will say, hang on, we have trim. What's the difference between trim and strip? And the answer is that trim uses a different definition of white space to strip. Strip leading and strip trailing all use the Unicode definition of white space, whereas trim just uses space, tab, and uline. In the case of the Unicode definition of white space, there's a whole range of characters you've probably never heard of. Like there's vertical spacing, horizontal spacing, things like that. My favourite new feature in JDK 11, it's a quite small one, is a new method on the predicate interface called not, which takes a predicate. How does that work? So if I use this where I'm filtering something and I want to filter out blank lines, so I can use the new method in string. In this case, the Lambda expression is going to be I take a string and then I remove ones that are blank. I can rewrite that using predicate not, and I can say filter predicate.not, and then I'll use the method reference string is blank. And if I do a static import on the predicate not method, I end up with filter not string is blank. So it just makes it, to me, it's more readable, clearer on what actually is going on. So it's a simple change, but I like it. Big thing in JDK 11 was the removal of a number of modules. So I mentioned that there is this idea of removing APIs as well as adding them. And so in JDK 9, the java.se.ee aggregator module was turned off. It was still there, but it was turned off. So when you compiled code or you ran code on the JVM, if you had used any of the APIs in these modules, it would fail to compile and it would fail to run. But you could then turn them back on again. Now in JDK 11, all of these modules have been completely removed. What has gone? Well, the java.se.ee aggregator module is really all the sort of enterprise type APIs that have snuck into Java SE over the years. Corba. Anybody using Corba? Ah, okay. Well, not developing any new code in Corba, right? No, okay. So Corba has gone. There aren't many people using Corba. Bean's activation framework, that's gone. JAX-B, the API for XML binding. Anybody using JAX-B? Interesting enough, the people in Italy seem to be using JAX-B more than I found in other places. And then the last one, which certainly in the presentations I've done, this one catches most people out, is JAX-WS. So Java Web Services, SOAP-based web services. Yeah, you see? Okay. Well, other than Corba, sorry, the other ones are fairly simple to replace. So if you're using Maven, you can just update your POM file, and there's a copy in Maven Central where you can download the necessary module from. Corba, it's a little bit more work. You have to provide the Corba module yourself. But they have all been removed from JDK 11. JDK 12, another 6 months of development. What do we get in JDK 12? Well, again, now we get some more interesting things in terms of the language. This is what I like with the new release cadence, is we are seeing small changes to the language coming through more quickly. And what we've got here is what are called switch expressions. And the key thing about switch expressions, firstly, is this is a preview feature. Now, preview feature is one that they want to introduce into the language, but they don't want to make it part of the standard straight away. They want to let people test it, give some feedback, and then if they need to make any changes, they can. But because it's not part of the Java SE standard, it's easier to make a change to it before it's actually set in stone. So the first of these is switch expressions. If you look at Java in the past, obviously we have switch. Switch is a statement. And a statement means that you can't assign the result of that statement to a variable because it doesn't generate a result. If you look at the way that the switch statement works, the syntax was taken pretty much directly from the C programming language. And C programming language is initially designed for systems programming, where you wanted to do certain things in a certain way, but that doesn't really quite translate into the way that application code in Java really wants to work. There are a couple of things about the way that switch statement works that do cause a few problems, if you like. First of those is the fact that you have to have every case statement needs to be separated out. Second thing, and probably more problematic, is the fact that you have to remember, if you want to put a break statement at the end of each part of your case block. And I know I've certainly forgotten to put a break statement in a switch statement in the past. And those are the kind of bugs that can be quite tricky to find because you end up with something happening because it drops through into the case statement below, and you go, that can't possibly happen. Why am I getting this value associated with that? And it turns out it's because you didn't put the break in and it drops through. And the scope of local variables can also be not quite as intuitive as it should be. So this is a very classic example of how we use the switch statement. What we want to do is we want to switch on one variable, and then based on that value, we want to assign something to another variable. Very common pattern for using the switch statement. It's kind of like a multi-if then else type thing. So I've got the number of letters as my variable, and then I want to switch on the day of the week. Depending on which day of the week, I want to assign the number of letters in the name. Monday, Friday, Sunday is 6, Tuesday is 7, and so on. If we look at that, the syntax of this is quite verbose. There's lots of lines of code there to do something that's quite simple. And again, because we have to remember to put a break in, that could lead to some problems if we forget to do it. And we have to make the assignment in every set of case statements. Again, if we forget to do that, we could end up with an error. With switch expressions, we can make that a whole lot simpler. So now we end up with this. Because it's an expression, we can assign the result of the switch expression to our variable and do that once. So we don't have to remember to do it in each case block. We also don't have to have an explicit break. That is implicit in the way the code works. And as we can see, the engineers at Oracle have done some research and they have found this incredibly powerful feature. It's called a comma separated list. And so now we're going to have a case Monday, comma Friday, comma Sunday. We don't have to have a separate case statement for each one. Yay, 25 years it's taken to find this. So now we have much simpler syntax. They borrowed the arrow operator from the Lambda expression, so the right-hand side of the arrow is the value that's returned from that case statement. Monday, Friday, Sunday, we return 6, Tuesday, 7, and so on. And we can also throw an exception if we need to. That's legitimate as well. Much simpler, much easier to see what's going on. We can combine old style with new style. Great. So now we can assign our variable. We can still have a separate case on each line, but in order to say what value is returned, we use break. So we go break 6, break 7, and so on. Now, break statements can be used with a label, but a label can't start with a number, so it's unambiguous. But we'll come back to this. And then you can also do this. You can make your life quite unpleasant. And you can do code blocks. So you could say case 1 and then you can have a code block, and case 2 and you can have a code block. The important thing here is that you can actually use variable x in both of those cases. In the old case statement, you couldn't do that. You had to have a different variable name in each case statement. So the scoping of it was only within the whole switch statement, not within a case. So now you can do that. I don't recommend that as a coding style. That just looks nasty to me. JDK 12, some selected JEPs. First is that Alexei contributed the Shenandoah garbage collector to OpenJDK, so that's now in there as well. Again, it's experimental, so you need the experimental flag turned on in order to use it. They made some more updates to the G1 collector to improve performance. First of those is a portable mixed collections. The idea there is that if the garbage collector is working its way through a particular phase of garbage collection, and the JVM notices that's taking an awful long time to do, it will actually abort that phase of the collection. It will say, okay, we've collected enough space now, go back to running the application code, so it reduces the overall pause times of the garbage collector. And quite useful is the idea of being able to return unused memory to the operating system. If you've got multiple processes on the same machine, then you get the memory back to allocate to other processes. JVM constant API, that's related to the dynamic class file constant, so there's now an API that allows you to access that from your Java code, and also related to class data sharing. There's now a default archive for the Java libraries, so you don't have to create that yourself. Streams has another collector. I quite like this one. So this is what's called teeing. And teeing is one that takes two collectors and a by function as parameters. And to kind of explain what that does, I've shown this diagram here. The idea is that we take our input stream and we duplicate it. So we have two exact copies of the input stream. We pass those input streams into the two collectors that we've specified, take the results of those collectors, and pass them in as the parameters to the by function, takes two inputs, and generates a result. So that is the result of the collector. To give you an idea of how you can use that, here's an example. So what I can do is I can take a stream of numbers, 145217, pass that into collect, and I use team. I say that the first collector I'm going to use is summing double. That will add up all the elements on the input stream. The second collector I'm going to use is counting, which will give me the number of elements I have on the input stream. Because we've duplicated it, we get the same inputs. And then the by function, I take that total of the values on the input stream, the number of elements on the input stream, divide one by the other, and it gives me the average. Now, I could have done that with a single method call, but it shows you how the team collector can be used. Clearly, more complicated things in terms of the processing. It's quite a nice, useful addition to the Streams API. JDK 13. So right now, this is the current release. Obviously until next month. But this is the current release. JDK 13, I'd have to say, was probably the lightest release yet. There weren't that many new features in JDK 13, but we did get text blocks. So this was something that was going to go into JDK 12. They kind of played around with it, had some ideas, but then they decided it wasn't quite ready, so they put it in JDK 13. This again is a preview feature, so it's not one that's cast in stone. And if you think about it, Java's always had a problem with strings that go across line break boundaries. You can't define a simple multi-line string in Java. Now you can. So what you can do is you can say 3 double quotes is the start of a text block, which can be a multi-line string. Everything after the 3 double quotes, including line breaks, is part of the string, up to the next 3 double quotes. If you want to put 3 double quotes in your string, then you have to escape it. But that's pretty much the only example where you have to escape. All the other text is simply treated as part of the string. If we print that out, we will see this. And you'll notice that that looks a little bit different to how the text is actually defined. The reason for this is because they needed to be careful about how they treated incidental white space. What you want to be able to do is to have the left-hand margin of your text lined up so that you have it where you want it to, but you can still lay out the code so that you can put it more on the right-hand side so that it fits in with where the string web page part is. So in this case, where the 3 double quote closing quotes are indicates how much incidental white space will be removed. So if we line up the 3 double quotes with our HTML tag, then that much incidental white space will be removed. What we could do is we could actually move those 3 double quotes to the left, and then that would introduce more space in front of the tags that we've got. So if we wanted to change where the left-hand margin was, we can do that. The way it is at the moment, it will actually add an extra blank line, but we could put the 3 double quotes after the HTML tag, and that would still remove the incidental white space. So it's just a couple of things to be aware of in terms of how text blocks work.
And will it be possible to use interpolation string? For example, substitute my web page with a variable that when I could substitute it when I use the system out to print a line. I don't know.
Yes.
Dynamic string, for example.
I don't think you do it with a dynamic string. No. Because you have to have the 3 double quotes.
Yes, I don't want to write on my web page, but I want to put
so if you put
a parameter, a variable that then I could substitute when I print a line, for example. No,
no,
it's not possible.
No.
But you can easily do it with the string formatter. So
yes.
you can do P rather than saying my web page. You do something like $foo.
Yes, yes.
And then you do string format, and then that is you can substitute $foo with.
And
whatever
is it possible even
yes.
with? Yes.
Yeah, because all this will do is create a string.
It's a string.
Yeah,
it's
yeah.
a pure string.
Yeah.
It's
Okay. Pure string. Exactly.
Okay.
And then
Do
you
not
can
change
do-
the string as
No,
a
exactly.
No.
string.
Yeah, so it's still a string. It just includes the line
Okay.
breaks and so on. So yeah, so I see what you're saying there. Yeah, and as you say, you can put the formatting things in there, and then you can use formatter with that.
Yes. Okay. Thank you.
Switch expressions. Hang on, I've talked about switch expressions already. Well, the thing here is that this is one of the really interesting things about how the preview feature works. It shows it does work. Because people said, hang on, if you use break with a number, that is confusing because you can break to a label, and even though a label can't start with a number, you could technically have break with a number, or you could have break with a label, and that just gets confusing. So they said, okay, we'll change it. So now you use yield. Yield 6, yield 7. So you don't get confused with breaking to a label, it's yield with a number. JDK 14. So
Is yield a new keyword?
no, it's a keyword, but it's where has the describe it? It's like position specific, so it only works in that instance. So there's no issue with using yield as a variable. Yeah, because it only works in that instance. So yeah, it's not a new variable, a new reserved word. No. So JDK 14, I thought because that's coming out next month, I would talk a little bit about the main new features that are coming in JDK 14. And I have to say that I'm actually thinking JDK 14 is looking really good because there are 3 features in there, and 2 of them certainly I really like. The other one's good, but you know the first 2 I really like. So the first of those is records. Yay! This just makes life so much easier. We finally have tuples in Java. The idea here is that if you want to have a simple class that contains a set of values, right now you've got to write a lot of boilerplate code because you have to create your class and you have to have, in the case of this, you do class record, then you have private int x, private int y, you have a constructor that takes x and y, then you have an accessor method for x, so get x, get y. A lot of code just to create a thing that contains 2 values. So records are a nice simple way of doing that. So now we can say record point, and we specify what values we want to store in there, int x, int y, and then just a pair of braces to indicate that that's part of the record syntax. Now records are inherently final. So you can't extend another class. It just has to be a class on its own. And they're final, so nobody else can extend it either. Also, the values that you specify here, int x and int y, are final as well. So there's no ability to change those values. What that will create is, in essence, the class that I just described. So it'll be a class that has 2 instance variables, x and y. It has a constructor. It has accessor methods, get x and get y. But you don't have to write any of that code. So literally 1 line of code, boom, done. Now, you can go a little bit further than that, and you can say, okay, let's assume that I want to have something like this, where I want to have a record called range, and that's going to have 2 variables, low and high. But actually, in my constructor, I want to be able to test to ensure that low is less than or equal to high. And if not, I want to be able to throw an exception. And the way that records work allow you to do that in a simplified form. So you can have the record still, say int low, int high, open brace, but now you can specify public range. You don't have to define it in the same way that you do a constructor. So you don't put the parameters there. Those are automatically assumed to be part of the constructor. And then you can say if low greater than high, throw a new illegal argument exception, bad value. You then also don't have to explicitly put in the this dot low equals low, this dot high equals high, which is what you would normally do in a constructor. In this case, again, the compiler will assume that because you defined it as a record, that that's always going to happen in a constructor. So this is a really nice little change to Java which allows us to finally have tuples.
Can I customize the equals and dash code?
Can you customize?
Equals and dash code?
I'm not sure actually. I have to check that. I have a suspicion that you can, yes. But, yeah, I have to check that. Because it would make sense, wouldn't it, to be able to
Use it as a key?
Yeah. I'll have a look at the Jeff in a minute, because, yeah, I would assume you can, because if you can replace the constructor, it would be very logical to be able to replace the code and the pattern matching, another preview feature. So records is a preview feature as well. What we can now do is we can extend the way we can use instance of. In the past, what we'd have to do is something where we say if obj instance of string, then we have to do a cast to a variable type string and then manipulate it. Now we get a simpler way of doing that where we say if obj instance of string, and then we give it a parameter name, a variable name as well, so we have string s. Within that if block, we can then use s, and we print it out, we can find the values from it and everything, and we know it is a string. But that only works in the scope of that part of the if statement. Within the else, obviously it's not a string, so we can't reference S outside of that part of the if statement. Again, just a simple change, but it's a really nice thing that simplifies stuff in terms of the code that we write. And then the last feature in JDK 14 I want to talk about, which is the one that I think is absolutely the best thing for a long time. Helpful null pointer exception. Now, has anybody here never had a null pointer exception? Yeah, right, of course. We have all had null pointer exceptions. But the problem we have with null pointer exceptions is that sometimes it's a little difficult to understand where they came from. Let's say we have some code like this. A.B.C.I equals 99. That throws a null pointer exception. And we get exception in thread main, null pointer exception. Okay, it's on that line. Great. It doesn't really help me because I don't know, was it A that was null, so I couldn't reference B? Was it B that was null, so I couldn't reference C? Or was it C that was null, I couldn't reference I? So I have to go back and I have to either use debugger or I have to put print statements in and separate it out and everything. In JDK 14, yay! Now, cannot read field C because A.B is null, and immediately we know where the problem is, and we can fix it. This is, again, it's taken 25 years to get to this point. How did it take that long? Surely this should be obvious. Yes, so again, really, really good feature, I think, in JDK 14, and I'm looking forward to being able to use that because I get non-pointer exceptions.
I think that the feature was in the backlog since the beginning, but
Probably,
we will fix it in the next release. We will fix it in the next release. And
I think you could be right, yes.
Was
the
it
second?
completed by a German company or something?
Yeah, I've got a feeling it was, yeah, because, I mean, other languages have had this for a long time, so it's not exactly rocket science.
I read that this feature was in the SAP, SAP,
yes, that's it, yeah, SAP.
Since 10 years,
Yeah.
something like that.
Yeah, that's right, yeah, it was SAP that contributed it, yeah. Other jets that have gone into JDK 14, there is a new packaging tool, which is, again, it's an incubator, so it's not sort of final yet, and that's because they took the old JavaFX packaging tool away when they removed JavaFX. Non-volatile mapped byte buffers is a different way of doing byte buffers and being able to manipulate those in a better way and have more efficiency around byte buffers. As I said, they've now removed the CMS garbage collector from JDK 14 and they've removed PAT 200 tools and API. Really, that's kind of related to applets, which have gone completely anyway, so I don't think anybody's going to miss PAT 200 too much. CMS garbage collector, maybe. Okay, just briefly to kind of finish off, talk a little bit about some of the longer term JDK futures. Obviously, we're seeing a nice kind of gradual change, lots of new language features and APIs introduced. What about bigger ideas for things in Java? One of those is Project Valhalla. And if you look at the way that Java works, it is an object-oriented language, but it's not a purely object-oriented language. Not everything is treated as an object. The reason for that is that when Java was created back in the mid-1990s, because of the processing power that we had in the amount of memory, it was deemed that in order to get the performance out of the JVM that they wanted, they couldn't treat everything as an object. So we had to have primitives as well. Simple representations of numeric values and booleans and so on. So we have primitives for performance, we have objects to give us encapsulation, polymorphism, inheritance, and so on. That comes with some limitations. Things like this, where we can't use a primitive, but we might want to. We can't do an array list of int. That doesn't work. We need a type in order for the generic to work. We end up with array list of integer, which is fine because that's a wrapper class around int. But we then get a problem of the fact that in order to use that, we have to create an integer object, we have to auto box the int into that object, we then put that into the array list, it takes space in the heap. When we want to use it, we have to take it out, we then have to unbox it and get the value out, and we have to do the garbage collection. So there's a lot of work just to store ints in an array list. People tend to try and work around that, so you end up with arrays of ints and doing all sorts of things like that. Valhalla, the way that they're going to do this at the moment with the current prototype is with the introduction of indirect projections. You'll have an array list of optional int question mark. I'm not totally convinced by the syntax yet, but that's the way they're going to do it. And essentially that will allow you to put an int into an array list without it having to be represented as an object. So the Valhalla will deal with the storage mechanism underneath. You can treat it like it's an array list of ints, and you get better performance in terms of storage and the speed at which you can retrieve those objects. Or values, I should say. The other thing that Project Valhalla is about is what used to be called value types, and then they've decided not to call them value types anymore, they're now calling them inline classes. And in order to do that, they're actually going to introduce two new bytecodes. So there is default value and with field. The idea here is again to have something that essentially looks like a class, but from a performance perspective and storage perspective, works like a primitive, like an int. Because of that, because it looks like a class and codes like a class, it can have methods, it can have fields, it can implement interfaces, it can use encapsulation, it can even be generic. But, this is very important, is you cannot change the values. So that's why they used to call them value types. In Java we have final. And final says, okay, you set the value once and then it's fixed. So technically you think, well, we can do that already. Except you can't, because a final value is not truly final. If you want to, you can change it through reflection. So it makes it not truly final. With inline classes, these will be truly final. There will be no way to change the value even with reflection. So it's absolutely fixed. And that makes life a lot easier when you're trying to use these things, because if you expect a value of 3 to be in your object, then that's what you want it to be all the time. You don't want somebody to come along, change it to 4, and then suddenly it doesn't work the way you expect it to. So you can't mutate the values, instance fields implicitly final, but also truly final. Can't be subclassed again because of the fact you don't want things change, and you can't synchronize on it because it's technically not an object in the way that JVM treats objects. Project Loom is the other one that's quite interesting, and the idea behind this is looking at how to make massively multi-threaded applications in Java. At the moment, each Java thread maps to an operating system thread. Once you get to sort of thousands, hundreds of thousands of threads, that doesn't scale. What Project Loom is about is having a number of Java threads map to a single operating system thread. And then the JVM will be responsible for scheduling and context switching those, as they're now called, virtual threads onto the operating system thread. Initially they called them fibers to distinguish them from Java threads, so you're going to have fibers as sort of lightweight Java thread. Then they decided that that wasn't a good way of calling it, so they called them lightweight threads. And most recently they've decided they're not going to call them lightweight threads, they're going to call them virtual threads. So that's kind of wrong. Now, I've said this here, it's JVM level threads, so does anybody remember green threads? Yeah, from right in the early days. It's not really green threads. Green threads was when you had an operating system that didn't support threads, like Windows 95, the JVM would actually put a sort of threading layer on top of it. What this does is add continuations to the JVM. A continuation is essentially the context that you need to execute code on a thread. It's the set of instructions, it's the set of values that you need in terms of registers and so on. If you want to do a context switch, you need to load a continuation onto a thread and make it run. So they're adding continuations to the JVM. In terms of the scheduler, they've decided that the fork join pool scheduler that's already been there since JDK 7 seems to work very well, fits very well with what they're trying to do, so they're using that at the moment. The idea, in terms of the prototype they've got at the moment, is much lighter weight than threads. It will use less memory, and they believe they can get close to zero overhead in terms of task switching. So it's looking very interesting in terms of having massively multi-threaded applications in Java. Just briefly mention Zulu Java because we're here and I work for Azul, so I'll just mention what we do there. We have what's called Zulu Community, and this is a free binary distribution of the OpenJDK. So it's very important to get that price point across, which is free. What we do is we take OpenJDK and we build that. So we create the binary distribution and then we run all of the TCK tests on that. And so that's about 150,000 tests that you need to guarantee that what you've got actually conforms to the Java SE specification. We have quite a wide range of different versions of JDK available. We actually go all the way back to 7 for our community builds. So we've got 7, 8, 9, 10, 11, 12 and 13. We've got early access version of 14 and even an early access version of 15, which doesn't actually have anything different in it at the moment. Wide platform support, so you can Intel 64-bit versions for Windows, for Linux and for Mac. And then for people who are using older operating systems like Windows XP, then we also have 32-bit versions for Windows and Linux. And we even have ARM 32 and 64-bit, so if you want to run it on the Raspberry Pi, you can. And you can get them for free from our download site. For those of you who would like to pay us money, which we hope there are many people, we also have Zulu Enterprise. This is our commercial product. Think of us like Red Hat for Java. So you've got the free version and then you've got a commercially supported version. What we do there is we actually backport all of the updates that Oracle produce into the older versions so that we can have those available for our customers very quickly after Oracle released their update. If we look at the update that came out in January, once Oracle had released theirs, we had our update available 26 minutes after they did. So it was pretty close. We'll try better next time. In terms of support, we're going to support JDK 8, Zulu 8 until March of 2026. So that gives you another 6 years of support for that. Right now, Zulu 6 is, so JDK 6 we're still supporting commercially, and that will be supported until the end of this year.
I think I saw until end of 2021.
Okay, yeah, I was going to say it may well be now that that's got even further now because people still want to use JDK 6.
Yeah.
In terms of our long-term support releases, we're following the same numbers that Oracle do, so 11, 17 and so on. And our idea is to have 9 years of active support where we will backport all the updates and make those available every quarter. And then there's another 2 years of passive support, which is where we won't provide updates on a regular basis, but if you have a problem, we'll still fix it and you can then get an update to that. We also have a thing called medium-term support releases. Because we said, right, you've got 3 years between long-term support releases. It could be that there's a really cool feature that you want to use between those releases. So let's say JDK 14 has got all these nice things in, you want to use that. So now 13 and 15 are our medium-term support releases, meaning we will provide updates to those until 18 months after the next long-term support release comes out. So that gives you 18 months to move from, let's say, 15 to 17. Just to summarise then, basically Java continues to evolve. It's nice to see that we're seeing lots of small changes come through. There are still lots of big ideas like Valhalla, like Loom. There's some other projects, Amber, Tala, Panama, various things like that that I haven't had time to talk about this evening. But there are lots of ideas to improve Java further. And one of the things that you do need to think about is which binary of the OpenJDK you're going to use. Oracle have changed the licensing for JDK 11 and also for the most recent updates of JDK 8. So you need to think about that quite carefully. And like I say, Zulu, Java, we can provide that as an alternative OpenJDK build at a very reasonable cost for commercial support. Otherwise, it's free. And with that, thank you. Grazie. So I don't know if anyone, I know we've had a few questions as we went through, but if anyone has any other questions, happy to take this.
I want to ask you something by the high level, because we saw the technical detail and feature. But I want to ask you, for example, your point of view about Java, because okay, you saw the past, you see the present, and you know the future, for example. And in my experience, I saw this future of Java in Scala, okay, 6 years ago,
Yes.
and now I see the same thing, for example, no, and so at the time Java was stuck, no, and now start to run, and now run fast, very fast.
Yeah.
And for you, what's the challenge, the goal for this run? Because I don't want to think like I don't know, Forrest Gump, for example, that start to run and then stop, and now we.
Yes, yeah. I think you see that if I think back in terms of the history of Java, when Java first came out, James Gosling always said that he looked at Java as what he described as a blue-collar programming language. It was one that was designed to get the job done. And so I think that the people like Brian Gertz and Mark Reinhold and so on have stuck very well with that goal. And they've sort of gradually changed Java. And they've realized that there are certain things that people want in the language. And, you know, sometimes it's taken longer to get those things into the language than people liked. But, you know, if you take JDK8, great example, the introduction of lambdas and strings gave us the ability to do a functional style of programming within Java without making it Scala. So it sort of took some of the best elements, if you like, of Scala and integrated those into Java so people could do that style of programming. Some of the things that we're seeing now are, you know, let's face it, we're borrowing stuff from Kotlin now, some of the features. And that's fine, you know, I'd like to see that because they look at other languages and they say, okay, this is a good feature, this is a good feature, let's bring them into Java. Java's still a very, very popular platform. Let's just add to it things that people want and keep it moving so it is still fresh in a way and people are getting.
And then track a line from the past of Java, because now Java wants to become not young because she had more years, but my thing is okay, they want to start a new life and not only use a surgery for okay,
just plastic surgery.
yes, it's true, it's they want to really restart with not a new language but with more experience in the past and start with a new story, for example. Yes.
Yeah, I mean, I think that, again, they're doing a very good job because things like Valhalla is going to be a big change, and that will add a lot of value in terms of the way that storage works and the way that you can do things. And by doing that, they're sort of staying true to the ideas of Java, so you've still got that compatibility. Okay, you know, they've removed a few things, but overall compatibility is very, very good. But they're still adding these big new features and making the language and the platform more valuable. And remember, a lot of the work is not just in terms of the Java language, it's also in the JVM, which does mean that languages like Scala, like Kotlin, like Clojure, and so on, can be compiled into bytecodes, and you can take advantage of the JVM as your runtime platform. You don't have to write everything in Java, you can use other languages. And again, that's a real valuable thing, I think, that they're continuing to do that.
Okay, thank you.
Okay.
Cool. So you mentioned you wanted to do maybe a second one, or
I can if you got something.
It's up to you.
I mean, I'm happy to talk about.
Se avete interesse possiamo fare, Simon può fare un'altra più dedicata a Java Performance.
Che ore sono?
Sono le 8:23.
E dobbiamo uscire alle 9 poi.
Sì?
Quanto
Can you squeeze it in
30
half
minutes?
an hour?
Yes, I can definitely do it like that. Yeah.
Ok, allora, non è obbligatorio, chi vuole andare o ha impegni eccetera. So we have kind of a exit, they close the buildings at 9.
At 9, okay, yes.
So,
Yeah, I won't be the least bit upset if people feel that they need to leave, so
No,
that's
that's
fine. But if anybody wants to stick around, I'm more than happy to talk about this for half an hour. Yeah.
or can I just...
Sure.
Chi è che è interessato a venire a cena dopo? Perché se siamo in tanti magari chiamo il ristorante e prenotiamo. Ci stiamo senza problemi. Voi venite? Vi interessa? Andate?
Yeah.
Dinner?
Italian food, yes.
Yeah.
Hopefully Italian food.
No, I mean, if everybody was coming, I had to call the
Sure.
restaurant and reserve it. It's fine. Cool.
Okay, so we talked about Java and all the changes that have been made to Java in terms of the language and so on. This presentation is about the other side of what we do at Azure. Now, don't worry, this is not a sales and marketing pitch. This is a technical presentation where I'll explain what we do to make our JVM work in a different way and give you better performance. So the first thing we need to talk about is speed in the Java world. And the reality here is that if you think about it, we've got the JVM. And JVM introduces this extra layer between our application and the machine that we're running on. So that's sort of something that's quite important. When I did this, I thought, right, I'll produce a graph that shows what we want in terms of the perfect performance of the JVM. And this is what I came up with. It's quite a simple graph, which says that what we really want is to start off at 100% of possible performance of the JVM, run at 100% of possible performance until we start the application. Great, well, it's not exactly rocket science, is it? No, but unfortunately, the reality is that when you run the Java application, you see something like this, where you start off with your application running quite slowly because of the JVM, and then it gradually increases in speed until we get to our 100% level. If we look at that in a little bit more detail, what happens is that when you start the application, you're using bytecodes. That's the whole point of Java, write once, run anywhere. Bytecodes are a virtual machine instruction set. They have to be converted into whichever platform you're running on. That's bytecode interpretation. That's a slow process, and every time the JVM hits the same bytecode, it does the same thing. So it's not doing anything clever in terms of caching or anything like that. It just interprets every bytecode every time. That's why when Java first came out, it was criticised as being slow compared to C and C++ compiled code. Developers of Java looked around and they said, how can we solve this problem? And they said, okay, there's this other idea called just-in-time compilation, JIT compiling. What that does is it says, run the application and monitor how many times you call each method. When you get to a certain threshold in terms of the number of times the method is being called, you say that's a hotspot in terms of code, hence the name of the JVM. At that point, the JVM will say, let's compile that into native instructions. So we get a performance improvement because now we're not interpreting every bytecode, we're actually running native code. To do that, it uses the C1 JIT compiler. And the C1 JIT compiler is designed to compile code very, very quickly, but doesn't apply a lot of optimizations. So we get an improvement in speed, but not a huge one. It will also, as the application continues to run, the JVM will gather profiling information about how the application is running with that particular method. When it gets to another threshold where it's been using that method a lot, it will recompile the code with another JIT compiler called C2. C2 uses all the profiling information that was gathered during the C1 phase and then compiles it with a lot more optimizations, all the optimization you can use. As we gradually warm up, we'll see some dips in performance. And those dips in performance are due to de-optimizations. Because one of the things that the JIT compiler will do is it will use speculative optimizations. And a speculative optimization is, let's say you have an if statement. So you've got two branches, true and false. During the C1 compile code, you may go through only the true branch of your if statement. The compiler will assume in the future that you'll continue to do that. So it'll optimize based on just the true branch of the if statement. If that carries on, that's fine, but you may hit a point where something happens and you go through the false branch. So then the compiler has to, or the JVM has to throw away that code, incorrect assumption, and then recompile it with both branches so that the code works that way. So we see some dips there. Then eventually we get to a steady state where all the methods that we need on a regular basis have been compiled by the C2 compiler and the optimizations have been eliminated. But we still see drops in performance. Those are due to garbage collection. Garbage collection kicks in and we get pauses. So the JVM poses some challenges because it is a managed runtime environment. It does garbage collection, and the thing about garbage collection is it is inherently non-deterministic. We can't predict when garbage collection will happen or how long it will take to do. Pause times can be big. So, if you're unlucky, you see pause times, it could be hundreds of milliseconds, they could be seconds. If you're really unlucky, it could be minutes for very big heaps and long garbage collection pauses. Biggest garbage collection pause I came across was a customer we had in the US, had a garbage collection pause of 1.5 days. That is an extreme garbage collection pause. I said to them, well, how do you even know it's still doing garbage collection? And they said, oh, we've got JMX instrumentation, we can see it's working. And then I said, well, why don't you just stop the application and restart it? And they said, it takes more than 1.5 days to load and process the data. So it's actually better off doing the garbage collection. So when we said we can eliminate garbage collection pauses, they were very happy. The other thing, as I said, big byte codes, not machine codes, the speed of warm-up, the adaptive combination strategies and so on, these are all things that need to be challenged. So what if there was a better JVM? There is. It's called Zing. So how does Zing work? Well, again, what we do here is we take OpenJDK source code. We start with the same hotspot that Oracle provide. And again, when we built our modified version of the JVM, we run all the TCK tests on it to make sure that it works in exactly the same way as a normal JVM from a functional point of view. It is a drop-in replacement. You don't have to recode anything. You don't have to recompile. You can use exactly the same class files. It doesn't have a problem with that. What we do is we replace all of the garbage collectors in hotspot, serial, parallel, G1, CMS, whatever, with one called C4. Now, the way that this works is it's actually only supported on Linux. The reason for that is that we have either what we call the Zing system tools, or we use some Linux-specific system calls to do memory management. So because of that, we only support Linux. Second thing we've done is to replace the C2 JIT compiler with a thing called Falcon. I'll explain a bit more about that as we go through. And the last thing we have is called Ready Now, which is to eliminate warm-up time as much as possible. Again, I'll explain what that actually does. Briefly talk about Zing system tools. If you look at Linux as an operating system, it has a virtual memory system that maps physical pages to virtual address space. That works very well, but it's designed for general purpose applications. What we did is we said the JVM is a very specific application. So we would develop a set of technologies that work at the operating system level and in essence replace the virtual memory system. They actually kind of complement it in a way so that we can get better performance in terms of the memory management. We can do some clever tricks like contingency memory, which allows you to actually go beyond the heap size that you've allocated and you won't get an out of memory error. I won't get into that too much detail because I need to keep this short, but we can do some clever tricks like that. Since August of last year, we've now done a version of Zing that doesn't require Zing system tools. This is quite useful because if you're doing microservices and you want to deploy it to a container, you don't have to deploy or don't have to install Zing system tools on the host beforehand. So you can just put your container there and it will work. You do still have to use Zing system tools if you want large heaps of 1 terabyte or more. So you'd think with microservices, 1 terabyte, that should be all right, shouldn't it? Except I had a customer I talked to last week and they go, yeah, we use 1 terabyte heaps in our microservices. It's like, really? Okay. Okay, I'm going to kind of move over this pretty quickly, but in terms of garbage collectors, there's lots of different options. There's parallel collector, CMS, G1, Shenandoah, ZGC. All but one commercial garbage collector will resort to a full compacting collection. At some point, garbage collector will give up and say there's too much fragmentation, or there's not enough free space, it has to pause all the applications and do a full compacting collection on the old generation. And that's the one where you see the long pauses for the garbage collection. So we have C4. This is the continuous concurrent compacting collector. And that essentially tells you what it does. Firstly, it's continuous. It runs all the time. Secondly, it's concurrent, which means it runs at the same time as application threads. We do not have stop-the-world pauses to enable garbage collection to happen whilst the application threads are paused. It is compacting, meaning we move objects around within the heap to eliminate fragmentation. And we do that concurrently, and we do it safely, and it collects garbage. From a sort of overview point of view, we use a generational heap. Same idea as Hotspot, we have a young generation and an old generation. But unlike Hotspot, we use the same algorithm on both. Now the reason that we do that is because our algorithm works really well, but having two generations is still very efficient from the point of view that most objects that you create are very, very short-lived. So if you can eliminate them in the young generation, you place less load on the old generation garbage collection. There is no stop-the-world compacting fallback, so you will never see that in our algorithm. And the algorithm we use is 3 phases: mark, relocate, and remap. And all of those phases can happen in parallel, so you can have multiple threads at the same time. The way that we can do this concurrently is through our loaded value barrier. This is essentially a read barrier that intercepts every access that you make from application code to an object in the heap. What we do is we intercept that and we look at some bits in the object header to determine which phase of the garbage collection we're in and what state the object header is in. That allows us to enforce 2 rules in terms of how the garbage collector works. First is that whenever we're in the marking phase, every object that you get in the application will be marked as valid, so it won't be garbage collected. Second thing is that if we're in the remapping or relocating phase, then you will get the right position for where that object is. If we're moving it around, you don't get the old reference, update it and lose the changes. Always get the right reference for that. So that allows us to do fully concurrent marking, fully concurrent relocation. Some people say, well, hang on, if you intercept every read to an object header, doesn't that place an overhead which degrades performance? And the answer is yes and no. Yes, it does, but what we're doing is looking at a bit in the object header. So we do 2 instructions, test and jump. And the idea is that if the bit is not set the way we want it to, we have to jump to a handler. But most of the time we're not going to do that because it'll be fine, and then we just go past that. That's 2 instructions, and if you look at the microcode in an x86 processor, that's 1 micro operation, which is about 1 nanosecond of overhead. That, if you look at the comparison between the time it takes to access L2, L3 cache or main memory, is so small that it makes no difference, no significant difference in terms of performance. So how does this work? When we start, we want to do marking. And the way we do that is by taking the same approach that many other algorithms do, which is to create a root set. The root set is all the objects that we have directly accessible from our application. We scan the stack, we look at the registers, we look at the static variables, and we build up a list of objects. Those objects will most likely have references to other objects, and those objects reference and so on. We need to build up a complete graph of accessible objects and mark them. So the garbage collector will come through and it will look at the root set and it will mark the bit in the object header to say that is a live object. Then we'll trace through from there, follow the object references, mark those objects as well. The root set can be divided up, and we can have multiple threads handle that in parallel, so we can do that work. Our application is still running, and so it may access an object that's not in the root set. Our test and jump looks at the bit in the object header and says, this has not been marked. We jump to the handler, and essentially what we do then is we let the application thread context mark the object as being valid. So we don't go to the garbage collector, we just let the handler mark that bit, and then we get back a reference to our object, and that's fine because we've enforced the first rule. Clearly, we also need to trace objects from there to make sure that those are marked as valid. But we don't want to do that in the context of the application because that's technically an unbounded task. So to get around that, we hand it off to the garbage collector, we make it part of the root set, let the garbage collector trace all the object references, and we guarantee that everything will be marked as valid that is still accessible. Then we need to do relocation. So we have our objects spread out through the heap, we have fragmentation. Object ABCDE, and we need to relocate those to make them contiguous in memory. We can calculate where those go, and we can say, okay, A goes to A prime, B goes to B prime, and so on. We can copy those objects to relocate them. And in order to do that safely, we'll put a lock around that copy operation. But because the copy is going to be very short, most objects are very small, the amount of time it takes to copy an object is very small, so you don't see significant pauses. So that happens very quickly, we have a lock for safety. We record in a side table all the information about which objects have been copied to where, so that we know where they've been relocated to. Another thing we can do, and this is where Zing system tools come in, is some clever things in terms of the virtual and physical pages. The reason for having this side table is that when we have copied objects from that block on the left, where we had A and B, to the block below, we know that we're never going to use that page in memory again. So even though the virtual address space is valid, we can actually say we'll steal the page from underneath it, so that we can then use that for the next page that we want to start copying objects to. This allows us to run the heap until it's literally almost full and do a full collection on it with only one free page per thread of garbage collection. So literally we can collect a full 8 terabytes of heap with only one free page per garbage collection thread. And then again, we can steal another page under there for that. Then we come to remapping, where we need to update the object headers to represent the changes that we make to where those objects are. So we've got our side table, our garbage collection threads then start working through that side table and saying that A needs to be updated to A prime. So we change the reference in the object header and we mark the bit to say that we've done that work. Similarly, we can do that with multiple threads, we can do it in parallel. The application threads are still running. So when an application thread accesses an object, it does the test and jump. It says, this object has been relocated, but it hasn't been remapped. So again, we jump to our handler. The handler will take the information from the side table, update the reference in the object header, and then mark it as being processed, hand it off to the application, so we guarantee that you get the right address for your object. So C4 is a truly pauseless garbage collector, and if you look at the typical worst case latency that you get, 10 milliseconds out of the box. So that's without any tuning, just set the heap size and that's what you get. Do a bit of tuning and we can get it down to typically below 1 millisecond. This will give you a very consistent latency profile. The latency won't change regardless of the heap size. 512 megabytes minimum, 8 terabytes maximum. No change in latency associated with larger heap sizes. Allocation rates we can keep up with 20 gigabytes a second, provided you've got a big enough heap to do that. Duration, you can basically run it as long as you like. So you're not going to have to restart it after a particular period of time. It will just keep running. So long as you don't run out of heap space, it will just keep going. Don't have to worry about memory fragmentation. You don't have to worry about the load profile. Talk a little bit about GC tuning. So GC tuning is a real black art, and there's lots of command line flags that you have to fiddle with to try and change the way the architecture works. And these are two examples of real-world command line parameters that people have set. And I don't want to go into all the details of this, but I will just point out one thing, which is that two different customers provided this, and they have both set the survival ratio. One set it to 128, one set it to 2. What's the right value? I mean, who knows? You know, it's a black art. So the problem is you end up trial and error. So you try 2, you try 128, you try 64, and you figure out what makes sense. But of course, that's only one parameter. You've got lots of parameters. So you end up with like an n-dimensional space to try and tune the best performance for your garbage collection. So let's look at the equivalent set of parameters that we would set for Zing. That's it. Just set the heap space. So it becomes so much simpler. All we have to do is set the heap space. Like I said, there are some other flags we can set. There's literally like about, less than 10. There's probably about 6 that you can set. But, you set the heap space, and then our idea of tuning the heap space is simply to go, okay, bring it up and down, find the level that works, where you've got enough to keep your application running, a bit of overhead, so when it needs extra memory, it's got it. But that's all you have to do. How can I show that this works? Well, what we've done is we've created this little open source tool called JHiccup. And JHiccup is designed to measure the latency of everything below your application. So we're not talking about latency of response to your application itself. It's what is the latency of the JVM, the operating system, and the hardware. The way it works is we put a thread alongside your application in the JVM. And we don't interact with your application, don't have to change any code, and we spend most of our time asleep. So it doesn't affect the performance of your application. When we start the thread, it goes to sleep for 1 millisecond. And when it wakes up, it looks at the system clock and says, I expect it to wake up 1 millisecond later. When did I actually wake up? If a garbage collection pause kicks in, let's say it's 20 milliseconds, then it will wake up 20 milliseconds later than it thought it would. We record that, and then we can generate some log files, histograms, and some nice graphs. Here's an example. So this is Elasticsearch running on a machine. Left-hand side is hotspot, right-hand side is Zing. This is running on a 128 gigabyte heap. If you look at the left-hand side, hotspot, that's a very typical hotspot garbage collection graph. You're seeing lots of small spikes, that's about 500 millis, which is half a second. And then you've got 2 big spikes. The small spikes are minor garbage collections, the big spikes are major garbage collections, older generation. If you look at the right-hand side, Zing. Now, bear in mind that high is bad. So you look at that and you go, ooh, hang on. Zing's all over the place. There's like big spikes, lots of spikes, and all sorts of stuff going on there. But I have been very deliberate in the way that I've presented these graphs because I have scaled the graphs differently. So on the left-hand side, we've got an 8-second scale. On the right-hand side, that's 80 millisecond scale. So if I change the scales to be the same, we get the desired effect, which is to show how Zing works. It eliminates all of the garbage collection portions. So this is exact same hardware, exact same application, just rerunning the same application with 2 different JVMs. Like I said, completely eliminates the problem of garbage collection. Just another example, this is Hadoop, and what I've done here is to scale the graphs the same. 5-second range, you can see that there's lots of stuff going on there with Hadoop. And then if we change the scale to kind of make it more obvious, okay, that's a 500 millisecond range, and still you're not seeing very much on the Zing side. And if we go down to 50 milliseconds as the graph there, we can see we're getting pretty much consistently in the sort of 5 millis range. We've got a couple of spikes there. Those probably spikes are not due to the JVM itself. There'll be things about the operating system that does context switching and stuff, which we can't actually avoid. But you can see the difference between hotspot and Zing in that case. Quickly talk about Falcon, because I've only got a few minutes. We decided to replace C2 because it was very old, and we wanted to try and improve performance of optimized code. So what we did is we used the LLVM project. open source project. It's designed for compilers, primarily C and C++ back-end generating code. So we replaced C2 with that. We integrated LLVM into the JVM, made it work as a JIT compiler, contributed code back to the project. Gives us much better performance. So some examples here. So this is a simple example of a loop, and most modern compilers, in fact all modern compilers, will look at that and be able to use vector operations for that. Vector operation is a wide register. You load up a number of elements from your array, then you can apply a single operation to all of them in one clock cycle. So it's a single instruction, multiple data. So that's an easy one for compilers to compile with vector operations. Make it a bit more complicated, add in some conditional operations, and compilers stop using vector operations. They can't spot the fact that that can be applied in terms of vector operations. So without going into too much detail, this is the kind of code you'll get from a traditional JIT, where it's not using vector operations. All it's doing to optimize is loop unrolling. So it's doing 2 elements per iteration of the loop to try and improve efficiency. If we look at the same code using Falcon, it looks a bit more complicated, but essentially what we're doing here is using the AVX2 instruction, so that's a 256-bit wide register, and it's doing 4 times loop unrolling. So the fact that we've got that gives us the ability to do 32 elements per iteration of the loop compared to 2 that we get for hotspot JIT compiling. That's the kind of thing where if you're doing numerically intensive operations, it'll give you way better performance by doing that. Just to talk about ready now, already shown you this graph, and the issue is application warm-up. Problem is you have to do that every time you run the application. Every time you start it up, you have to go through the same process. What we do is allow the application to warm up and then record a profile. The profile consists of the classes that loaded, classes that initialized, all of the profiling data that was collected by C1 compiled code, and any of the speculative optimizations that failed and needed to be de-optimized and recompiled. We can collect that information over a much longer period of time. You don't have to wait a couple of minutes, you can wait a couple of days, a couple of weeks before you take the profile. So when you're happy with the performance, you can take the profile. What that allows us to do is when you start your application, is we immediately load all the classes we can load, initialize all the classes we can initialize, and then compile the methods that we need using the profiling data and the speculative optimizations that failed, so that by the time you get to your main entry point, we've compiled pretty much all the code that you're going to use. And so you get about 98% of the performance you had when you start the main as you had when you took the profile. Roughly speaking, you need 1 or 2 transactions just to sort of push it to that 100% level of performance that you get when you want to do that. So again, looking at a graph, this is a simple application. Before using ready now is the orange, where you go up and down. That's the de-optimization, re-optimization, compile, and so on. With ready now, you just get a nice flat line again. So it eliminates a lot of the problems there. The last thing we've done is compile stashing, because if you look at the way that things work with ready now, we have to do all this work before you get to the main entry point, and that delays the start of the application. Even though the application is starting very fast in terms of its performance, it's delayed how long it takes to do that. So it's easy to show you a graph. So without ready now, we've got our warm-up. With ready now, we see this. So we get a much steeper graph, but we've got this kind of blank bit where the application is not able to do anything because we're doing all the class loading, initialization, and compiling. Compile stashing allows us to record all of the compiled code that we had when the application profile was collected. Now we can't just load that by default, it's a bit more complicated than that. But the way that Falcon works is that we take our bytecodes and we convert them to the LLVM intermediate representation. And then we pass that to LLVM to compile. LLVM needs to ask questions of the virtual machine to understand some of the things that have happened, to which it gets responses. It uses that information, compiles the code, optimizes it, and then generates the code to use. We have a fully deterministic compiler, which means that if you take the exact same set of bytecodes, which generate the same intermediate representation, and you take the same set of queries and responses that the JVM needs to answer, given those as identical input, we know that the machine code that's generated will be identical. So there's no difference depending on when you compile it. What that allows us to do is to put our compile stash, which is all the compiled code, between the JVM side of things and the LLVM side of things. If we get a match in terms of our intermediate code, intermediate representation, our queries and responses, then we just use the compile stash as a cache and we can take the code straight away. That takes us from this idea of having the pause before we start the application to a much shorter pause. So we can reduce the amount of compile time by up to 80%, and we can reduce the CPU load by up to 60%. So that kind of gives us the best possible combination of things in terms of starting up the application. So just to summarise, since I've done well. So essentially, if I overlay the two graphs here, we've got the graph that we saw, which is reality with hotspot, and then we've got the graph that we want in terms of our perfect graph. What we've done is use C4 to eliminate the pauses of garbage collection. We've used Falcon to actually raise the level of performance that we can get from the application itself. And then we've used Ready Now and compile stashing to move that envelope out so that we can eliminate as much as possible with warm-up time.
Is it Ready Now similar to application class data sharing?
It's a little bit like that. But application class data sharing is only one small part of what we do in Ready Now.
Okay.
So essentially, yes. I mean, we can use application class data sharing as well, because that then complements what we're doing. And in fact, we don't use it at the moment, but that's one of the things we're going to integrate fairly soon, is application class data sharing.
Thank you.
So the idea of the thing is to start fast, go faster, and stay fast. Like I say, very much a simple replacement for JVMs. You don't have to recode, and you can try it free for 30 days. You can go and download it, install it, go with it, use JDK, generate some nice graphs, and go, yes, that's what we want. And that's it. So I think we've just been in time. Grazie.